Before we start this analysis of the coding strategy, we need a small lemma which we need for this analysis. This lemma is directly a corollary of one of the theorems we had in the first section of the lecture, so in this first section of the lecture notes. So we need a result concerning Markov chain. So we assume that X, Y, and Z form a Markov chain. And then we suppose that Xn and Yn are jointly typical. And that Xn, Yn, and Zn were emitted by the discrete memoryless source Pxyz. Then we know about the probability that Zn is in the typical sets under the condition that Yn is equal Yn can be written in this way because of this Markov chain here. So we can add here the condition that Xn is equal Xn because it doesn't change the probability here. But this probability we know that was already in one of our theorems in section 1. So we know that this goes to 0. That was our, we called this delta epsilon 1 epsilon 2 of n. And so we know that this is greater or equal 1 minus this delta. You can write this delta in more details here. I think it's not so important here. So we just have to know that the right-hand side of 91 goes to 1. We need this for one of the cases we analyze now. Now we want to analyze our coding strategy. So we have to show again, if we are successful, then the distortion is smaller than d, the expected distortion. And if we are not successful, that then the probability of error goes to 0 if n goes to infinity. The first thing is easy, so we suppose that Xn and Yn are not jointly typical. This we know, of course, it goes to 0. That's also first section of the lecture notes. Okay, therefore we can assume that Xn and Yn are jointly typical. But now we can assume that the encoder cannot find a pair W tilde and V tilde such that Xn and Un of W tilde and V tilde are jointly typical concerning X and U. This is in principle but the same we studied already if you look at rate distortion for single source. And then we analyze this and we got as a result that R plus R prime have to be bigger than the mutual information between X and U. So we just can copy the proof of this. The next case is again, so Xn and Yn are jointly typical concerning X and Y, and the encoder finds a pair W and V such that Xn and Un is again jointly typical concerning X and U. However, our V tilde is not equal V. And now we have to restrict our bin somehow that this goes to 0. So look at the probability of this event. So that's the probability of the union of all V tilde not equal V such that Yn and Un is jointly typical. This can be written as a sum by the union bound. So we just estimate this as a sum, like if all this is equal, if all events are independent, of course. But of course, we can estimate it every time by the sum here. But for this probability, we know that the probability that Yn and Un is jointly typical is equal to 2 to the n times minus the mutual information plus 2 times epsilon the entropy of U. And we can estimate every probability, every event here by the same probability. And then we have a sum of always the same probabilities. So we look just how many summons we have. And of course, we know how big is one bin. One bin has the cardinality 2 to the n r prime. So we can estimate this by 2 to the n r prime times 2 to the n minus mutual information of u and y plus 2 times epsilon 2 and the entropy of u. Putting this together, we have that this probability, this error probability, is smaller than 2 to the n times r prime minus the mutual information between u and y plus 2 times epsilon 2 times the entropy of u. But we want that this goes to 0. So we can choose the bin. And now if we choose the bin smaller than the mutual information between y and u, or u and y, it's the same, then of course this goes still to 0 if n goes to infinity. So this is the second condition we have now, that our bin should not be too big. It is bounded by the mutual information between y and u, because then this event could not happen, or the probability of this event goes to 0. So the fourth case, again, we assume that xn and yn are jointly typical concerning x and y, and the encoder finds a w and v such that xn and un are jointly typical concerning x and u, but the decoder cannot find a v tilde such that yn and xn and un is jointly typical concerning y, x, and u. This is now, if we look at this is exactly the opposite event we have here. So that's this here. And here we know the opposite goes to 1, and therefore this event have to go to 0. So we know that this event goes to 0. So finally, we consider the event that everything goes well. So this is jointly typical, and v hat is equal to v, and then we can bound the distortion and follow. So now we have to see look that the expected distortion is smaller than d. So let's look at the distortion. In general, it's defined in this way. It's a per letter distortion as we define this. This, of course, this x hat is just the function of ui and yi. And this we can sum in another way. We just count the numbers of a, b, and c's in x, n, un, and yn, and look then at dA and f of b and c. That's just the same, just we sum in another way. And now we now apply the definition of jointly typical. And of course, we just insert here, for this, we insert the probability of x, u, y, and a, b, c, 1 plus epsilon times dA f of b and c. That's just inserting the definition of jointly typicality for 3 variables. Now we look at this, but this is exactly, if we put, so this times 1 and this here is the expected value of the distortion plus epsilon times d max. So we can of course, we can bound this by d max. That's one assumption we do have in general, that we can bound this with some d max. It cannot be infinity. And so we have the condition that in this case, the distortion is smaller or equal than the expected value of this distortion here. That means we have, as a result, so we have this weight region, this weight RVZ of D, and we take the minimum of the mutual information of XU minus YU, such that we can choose this artificial channel here in such a way that the expected distortion is smaller or equal D, where U, X, and Y forms a Markov chain. So look at here at the condition So we have the condition that R plus R prime is greater than the mutual information between X and U. We know that the bins cannot be so large, so we can bound the bins by the mutual information between Y and U. For this reason, we get here this difference between these two mutual informations here. And then, of course, we can choose this channel as we want. And then with our condition, we saw here that if this is smaller than D, then our distortion, of course, is smaller than D. So we need in the condition here that the expected distortion is smaller equal D. Then we know everything is fulfilled here. There's one remark. So we didn't make a bound for the cardinality of the alphabet when we choose this artificial channel between X and U. But there's Katadori's theorem, and which shows that just the cardinality of the alphabet can be bounded by X plus 1. And so we need just one symbol more for this alphabet to make this artificial channel here. That's enough. So that means this is our result. And we now have, of course, to prove the converse. So we know that we can assume this rate here. And now we have to prove the converse.